Hello, 107 students. We're back with chapter 2, which is a long chapter. And here we go with our next video. So let's go back to metals and nonmetals. Now in this periodic table, which you've seen earlier in this chapter, just wanted to remind you, the metals are blue, hydrogen and the pink elements are nonmetals, and then the yellow elements are the semimetals. Notice how this periodic table is numbered. It has 1A, 2A, and then it skips over to 3A, 4A, 5A, 6A, 7A, 8A, kind of how I numbered your periodic table, 1, 2, 3, 4, 5, 6, 7, 8, those columns. So again, I talk about the A columns. All right, so we saw that earlier. Just remember your metals versus your nonmetals, and that covalent compounds that we're talking about with our Lewis dot structures are made out of nonmetals. Okay, so we only do Lewis dot structures for covalent compounds, which are made out of nonmetals. Now, grab your shapes table that I mentioned at the beginning of this chapter. We're going to talk about the shapes of these covalent molecules. So the theory is called valence shell electron pair repulsion model, or theory, VSEPR. So electrons are negatively charged. And so electrons don't like to get close because it's hard to push negative things together. So negative things repel and push apart. Electrons repel and push apart, and this gives rise to the three-dimensional shape of our molecules. This one isn't on your table, but it's pretty easy. If you only have two atoms like Cl2, the two green atoms, they're just connected by a straight line. So we call it linear. So chlorine, oxygen, nitrogen, all of those diatomic elements, have no fear of ice cold beer, are linear in their shape. Linear for two atoms. If there's two atoms, it's linear. Now, for the rest of the shapes, we're going to have three or more atoms, and we'll look at the Lewis dot structure and match it up to something on our shapes table. Now, the notation I've given you in the first column is something we don't really have to look at too much, but A is the central atom, B is an atom attached to the center atom, and E is a lone pair on the central atom only. So we're only looking at lone pairs on the center atom to determine the shape. If we have three atoms in a straight line, that is also linear. It's called AB2. So we have two atoms bonded to a center atom, and if they're in a straight line, we call it linear. That bond angle is 180 degrees, and that is the first line across our shapes table. So it looks like this picture, then it's linear with a 180 degree bond angle. An example is CO2. There's a Lewis dot structure that I would give you, and you would say, aha, three atoms in a straight line, it's linear. All right, trigonal planar. This is when we have three atoms bonded to a center atom, and there's not any lone pairs on the center atom. So like CHHO. It doesn't matter that the bond to the O is a double bond. That's okay. It's still one atom O. So we have three atoms bonded to the carbon. So if you connect those together, it makes a triangle. Also, it's flat, which makes it planar. Planar means all the atoms could fit in the plane of a piece of paper. It's flat, like a pancake. Flat means planar. So let's look at our second row on the shapes table. AB3, if it looks like this, three atoms bonded to a center atom, it's trigonal planar, and the bond angle is about 120 degrees. Okay, so trigonal planar, 120 degrees if you look like this. Next, AB4. This is when we have four atoms bonded to a center atom with no lone pairs on the center atom. Now, we draw it the way I drew it there with the C and the four H's around it. Now, that makes it look flat, but that's how we draw it on a piece of paper because a piece of paper is flat. What it really looks like is this gray and white model. Do you see how it's three-dimensional? And the bond angles are 109.5, not 90 degrees. We call this three-dimensional shape tetrahedral. Let's look at the third row in your table. AB4 looks like this. 4 atoms bonded to a center atom. Name of the shape is tetrahedral. The bond angle is 109.5. So if you have 4 atoms bonded to a center atom, it's tetrahedral 109.5. Next. All right, AB2E. This is when we have 3 atoms, but we're not straight across. We're bent at an angle. So the name of the shape is actually bent. I always make fun of that because I don't think that sounds very scientific, bent, but no one asked me. So when you have 3 atoms, but they're not in a straight line, they're bent. So if you notice in the SO2 picture, there's a lone pair on the S. And so that's why this is called AB2E. E is electron lone pair. So we have a lone pair on the S, and that pushes those bonds down and causes it to bend. So if I give you 3 atoms, but they're not in a straight line, they're bent, and there's a lone pair on top, then you know the shape is bent. Just like it says here, AB2E, look at it. It's 3 atoms with a lone pair on top causing it to bend. It's bent. The bond angle's a little less than 120 degrees. Next, AB3E, trigonal pyramid. Now we draw it on a piece of paper the way it's there, N with the 3 H's and the lone pair on top. So NH3, it looks flat, doesn't it? But it really looks like this blue and white model. It is a little pyramid. The blue atom is sticking up above the white atoms. So it's a trigonal because the 3 atoms make a triangle, but the blue atom's poking up. So it's a triangle pyramid, trigonal pyramid. And the bond angles are a little less than 109.5. So again, this is called AB3E. It's here on your shapes table. If your picture looks like this, it looks like a little pyramid with a lone pair on top. It is trigonal pyramid, and the bond angle is a little less than 109.5. And the last one, AB2E2. Now this one's also bent. It has 3 atoms that are not in a straight line. So how can you tell it from the other bent? Well, the number of lone pairs. This one will have 2 lone pairs on the center atom. That's why it's called AB2E2. Remember, E is electron lone pair, and there's 2 of them. So water's an example of this bent. See, we have the H2O model with 2 lone pairs on oxygen. So that really makes it bent. The bond angle is just a little less than 109.5. So that's the bottom row, AB2E2. It's bent, but we have 2 lone pairs on the center atom. It's called bent, but the bond angle's different from the other bent. The bond angle's a little less than 109.5. So, summary. Given a Lewis dot structure of a covalent molecule, you should be able to 1. Determine if the bonds are single, double, or triple, and how many there are in the structure of the molecule. 2. Determine how many lone pairs total are in the structure, if I ask. 3. Use your shapes table and determine the shape and bond angle of the structure I give you. Okay, so practice some of those at the end of chapter problems, and good luck with that. See you in the next video. Bye, Kim 107.